Welcome everybody, and thank you for joining me today to learn about the fundamentals behind deep learning. Now, given the prevalence of deep learning and its applications all around us, I see that the material that you'll be learning today as being extremely important for your professional development, and I'm thoroughly honored to be a part of it.
Before we jump into the tutorial, I would like to first make sure that you are all set up and ready. Firstly, you should have access to the tutorial repository, which is located on GitHub at github.com/ericmjl/dl-workshop. We've linked the URL in the video description below. Once you go there, you should see the instructions for getting set up. At this point in time, you'll want to do one of two things. You can either follow the Conda environment setup instructions and host the Jupyter server locally. That's these instructions down over here. Or you can just click Binder, which is this little badge over there, and launch a Binder instance. This will bring you to a cloud-hosted, Docker containerized environment, which has everything set up for you. So it's really for those who are feeling lazy. And I'm going to use Binder to do the teaching as well, so you can opt to do so and follow along. Let's go. Once Binder has loaded, you'll be brought to an interface that looks like what I have on my screen. The most important directory inside here is the Notebooks directory. Go ahead and click on that. Inside the Notebooks directory, you'll find the main notebooks that we will use for today's tutorial. There are two versions, one being the instructor version and the other being the student version. Naturally, you'll be using the student version, as in there are the exercises for you to fill in. The instructor version contains all of the answers, so if you're stuck on something and can't figure out how to do it, do feel free to open up the instructor notebook and reference the answers in there. Let's go ahead and open up the student notebook.
Now, for those of you who are using Binder, here is a little gentle reminder. Binder has a 15-minute timeout. What this means is that every so often, possibly once every 10 minutes, make sure you execute something inside your Jupyter notebooks. This makes sure that you don't get disconnected, therefore losing all of the progress that you've had to date. Great stuff. Now that we're in the notebook and have everything set up, let's get started with the course. Let's first talk about the goals, prerequisites, and structure of the course. This way, you'll know whether you're prepared for it and what to expect of yourself by the end.
The goal of this course is to help you to understand that the basics of deep learning can be placed in the framework of model, loss, and optimizer. By the end of this course, you'll be able to provide a definition of these as well as examples. To help us understand these ideas, we're going to start by exploring them in the context of linear regression. This will take up about half of the course. Once we're properly grounded, we will progress to logistic regression and finally, feed-forward neural networks. By the end, you'll see all three components, model, loss, and optimizer, in action. Some familiarity with the NumPy API is necessary to do this course, as we'll be using a package called JAX, which builds upon the NumPy API and provides extras like an automatic differentiation engine. Having some linear algebra knowledge, mostly how to do dot products and nothing much more, will definitely be helpful. That said, if you're feeling rusty, the NumPy API is an excellent way to refresh your linear algebra knowledge. Finally, basic knowledge of Python data structures and flow control is necessary, as we'll be using Python exclusively in the course.
Now that you know what you're in for, let's get started with linear regression.
Linear regression, it's that first model we learn in high school math and physics. This equation that you see on the screen shouldn't seem too foreign to you. Y equals mx plus c, or wx plus b, whichever your notation is. I'd like to invite you to write down one problem where you might have used a linear model before. What assumptions went into it? Go ahead and think about it for a moment and pencil down your thoughts. Linear models are incredibly useful because they encode a structural assumption that the outputs are a weighted sum of the inputs with a bias term added in. Now, much of the world isn't linear, and in many applications, linear models would be an extremely naive assumption. That said, one thing I heard before is that if you zoom in hard enough, everything looks kind of linear. Now, with a linear model in hand, we can simulate the data that this model will generate. On the other hand, if we flip the problem and state that we were given data generated from a linear model with unknown parameter values w and b, then the task at hand that would be interesting is figuring out what parameters w and b best explain the data. Therein lies the definition of learning in deep learning. The learning here is figuring out what parameter values best explain the data for a given model. Let's take a look at this in action by explicitly simulating data and working through the multiple ways of recovering the parameters that generated the data. Come and code along inside your notebooks. Firstly, go ahead and complete the exercise on my screen that you can see on my screen, where we simulate some data generated from parameters that you get to decide. In my case, I'm going to do something like w_true is equal to 3.14 and b_true is 2.72 and y is equal to w_true times x plus b_true. We'll plot those guys. Oops. Do need to run everything above. There we go. And so there you go. We have some generated data, some ground truth data. Also, one thing we should do is we should add a bit of noise there. So let's go add some noise and let's go noise of len of x so that we have a single noise term per x per data point. And there we have it. We have our noisy generated data. So what we're going to do next is we're going to plot what we would consider to be a very bad estimate of w and b. So clearly I put 3.14 and 2.72. So let's do something like 6.28 and minus 42. And then we do y_est is w times x plus b. And let's plot those two over one another. And you can see how clearly bad that model is for the generated data. Now visually, we know that this model is extremely bad. How would we quantify this? One way to do so is by devising an error function or a loss function that tells us how bad the model is with respect to the data that we have observed. One loss function that we can use is called the mean squared error, which is defined as the average sum of squared errors. Visually, mean squared error looks something like this. In red, we have our actual data. Actually, I'm going to change all of that to blue to match the color scheme that we have inside our notebooks. In red, we have the model. Mean squared error is calculated this way. Let's backtrack a little bit. We also have the x and the y axes. Mean squared error is calculated in this way. Take the ground truth value and calculate its distance to the model on the y-axis only. Because we have 4 of these on this example, let's label them D1, D2, D3, D4. D is defined as D is the residual, or the difference. And the difference is taken between the model and the actual data. And it's subscripted by I to indicate for each data point. All right. Then we take the square of all of the data points, all of the differences. So that's this little guy that we want to put our focus on. And then we divide it by the number of data points that we have. So let n be the number of data points. Oops, that should go inside a marker. Where n over here is the number of data points. Now that you've seen what the mean squared error is, let's go ahead and implement it in NumPy. We've defined here the skeleton of the code. The function name is MSE, and it takes in two NumPy arrays, yTrue and yPred. Now, in the interest of good coding practice, let's go ahead and annotate the types of these two function arguments so that we can make the function a little clearer to read. yTrue is expected to be a NumPy array. yPred is also expected to be a NumPy array. And at the end, we're going to return some form of a scalar number, but it'll still also be in the form of a NumPy array. If you remember what the steps are, we need to write the difference, or the residual, between the two arrays. So D is equal to yTrue minus yPred. Then we need to take the square of them. So the square of the differences is np.power of D to the second power. And finally, we need to take the average. So let's call the average loss. np.mean of squared D, and then we'll return the loss. Now, there is a more compact way to write this. Once you get used to writing NumPy code, this is a very useful thing for you to know. So, return np.mean of square D. Yes, that's exactly what we want, but we can also replace square D with that, and we can also take D and replace it with the original. And so now we have a single line that accomplishes exactly what we want to do. Now, of course, granted, this is a little easier to read. But if you're well-versed with NumPy, feel free to write code like this. It's really powerful. All right, so in the interest of brevity, I'm going to comment out this piece over here, and we're going to use that one over there. If you calculate the mean squared error, you'll notice it gives us a number. Now, pop quiz. Should this number be positive or negative? Now, if you said positive, you're right, and that's because of np.power. The second power of any number is always going to be a positive number. Now, ys over here is the model prediction, and y is the data. So by quantifying the mean squared error between ys and y, we have quantified how bad the model is. What this does is open the door to optimization of the model. And what this means, simply, is tweaking of the parameters until we optimize, usually meaning minimize, the error or the loss function. Let's scroll down now and get a feel for this in action, first by doing it manually. Go ahead and execute the next code cell. That should provide you with an interactive set of widgets that you can use to tweak the values of w and b until you get the best fit model. While you do that, notice how the loss changes as the model fit changes as well. As you were optimizing the model, what did you notice about the MSE score? Did you notice how, as you approached the optimal value, just as I'm doing on the screen, the loss decreases, but as soon as you overshoot in the wrong direction, in the same direction, the loss increases again? Well, to understand this, we're going to take a detour into gradient-based optimization. Implicit in what you were doing just now is something we formally call gradient-based optimization. And this is a very important point to understand because gradient-based optimization basically underpins all of deep learning. If you get this for a linear model, you will understand then how it works for more complex models. So today, we're going to go into a small crash course detour on what gradient-based optimization is. So let's start off with what gradients are. Gradients. Gradients are related to derivatives. And at the risk of ticking off mathematicians with a sloppy definition, we're just going to say that for today's purposes, a derivative is how much our output changes as we take a small step on the inputs, taken in the limit of very small steps. So, how much our output changes over how much our input changes as delta x goes towards 0. So if we have a particular function, I'm going to define an arbitrary function. Let's say we have a function, so example here, we have a function, f of w, and it's as follows: w squared is equal to, f of w is equal to w squared plus 3w minus 5. From first year calculus, we know what the derivative of this function would be, f prime w, which is also known as df by dw, will be equal to 2w plus 3, right? And so when we talk about optimizing this function, usually what we refer to is find minima that's right, minima or maxima. I'm going to color these differently so it's emphasized over there. And more importantly, we want to find value of x. In our case, w for this function that maximizes or minimizes the output. So we know now that the minima of the function is present when the slope is equal to 0, right? So if we set df by dw to be 0, then we can analytically solve for what the value of w is that minimizes the function. So when df by dw is equal to 0, f of w is minimized, And so we can solve for it. And that would be our answer. Now, we know again from first year calculus that we can take the second derivative just to double check that this is indeed the minima. So second derivative tells us whether it's the minima or maxima. So if df by dw is equal to 2w plus 3, then the second derivative would be that, which is equal to 2, and 2 is always greater than 0, which therefore means this point is a minima. We have the form of, it's a smiley face. By counterfactually, if it was a negative 0, then we know that the function is a frowning face. And so therefore, we can tell that the point in this particular case would be a maxima. But we've got a minima point because our function is a smiley face, and therefore we've definitely found analytically what the minima is. Now, you can do this for simple functions, but if you're going to do this for complex functions, if you're going to do this for complicated functions, complex is an overloaded word. If you're going to do this for a complicated function, that's going to be a little bit more difficult, especially if you want to do this by hand, or if you're like me and a sloppy mathematician who can't copy equations properly. So, what do we do in this particular case? Well, that's when we can do this thing called computational minimization. And that's what we're going to go into next. So, what do we mean by computational minimization, or more generally speaking, computational optimization? What we mean here is to use information about the derivatives of a function, that function being the one that we want to optimize, to perform this optimization. Let's look at this pictorially to help us gain an intuition. If we pick any point on the number line for w, let's say we pick this point over here, and we evaluate the function at that point, we get another value. Now, we know that it is possible for us to calculate and evaluate the exact value of the gradient at that particular function. That gradient will look pictorially something like that guy. All right? This gradient will have a positive slope. What this implies is that it tells us to increase f of w, move in positive direction of w, delta w greater than 0. Counterfactually, if we took a point over here and evaluated the gradient at that point, this line over here is always less than 0. And what this tells us is to increase f of w, move such that delta w is less than 0. That is, we subtract. We need a negative gradient. We need to move negatively in the direction of w. We need to move w in the negative direction in order to increase f of w. That's what the gradient is telling us. Well, as it turns out, we don't want to increase w. Increasing f of w is not our point. Decreasing f of w is our point. So if the gradient is telling us move in a particular direction, well then all we have to do is move in the opposite direction to get to the minima. So in other words, we don't want to do this. We instead want to do this. Or if we were on the other side, we'd want to do that. Okay? And that is what we mean by gradient-based optimization. Now, one thing that we will do is we want to take small steps in the negative gradient. We don't want to take large steps because you can imagine if I took a really large step in this direction, vroom, we'd overshoot the minima and we'd end up on the opposite side. And if we took, again, a really large step on this side, boom, we'll be back out over there and we'll never hit the minima. So the goal here is we want to take, instead, really, really small steps like what we're showing over here and over here. All right? So now let's see how we can do this small step gradient-based optimization using Python code. Let's get started by first implementing that function that we've been using, that w squared function, as a Python function. So we'll do this, return w to the power of 2 plus 3w plus minus 5. Now, so in this code cell, we won't use it, but it's just there for us to keep a reminder. Now, we're going to do the next exercise, which is to write the derivative of f with respect to w. This also should be not too difficult. 2 times w plus 3. Now let's start. Once you've written that down, let's now pick another number to start w at. And I'm going to start with some ridiculous number, 3 times np dot pi. And we're going to do this thing now where we adjust the value over a number of small steps. In this particular case, 1,000 small steps. We're going to take those small steps in the negative direction of the gradient. All right. So how do we do that? For I in range 1,000, w is equal to w minus the derivative function evaluated at that particular value of w times a small number. And just so you know, 0.01 is an arbitrary number chosen, which is the step size taken. I'm going to have you also keep a history of w, all right? So we'll do this where we go history is equal to an empty list. My apologies, keyboard malfunction. And then we're going to do history.append w. And what we're going to do first is we're going to execute this entire cell. So let's go ahead and do that. All right, and we should reach some value, which is extremely close to the value that is the minima of this particular function, right? And barring some numerical precision error. And just so you can check that we indeed have minimized, we've changed the value of w and approached the correct endpoint over time. We're going to plot that. Import matplotlib.py plot as plt.plot history. And if we run that cell, you'll see we have gradually started from 3 times the value of pi to the actual value, negative 1.5. Now, if you think this will help you, feel free to pause the video and pick another starting point of w and rerun the code, and just confirm for yourself that you will always end up at negative 1.5 or somewhere really close to there. Congratulations! With that, you've just implemented gradient descent by hand. Gradient descent is what we would call an optimization routine. I'm hoping that this simple example makes clear for you how to use gradient-based optimization to optimize an arbitrary math function. Now, if you've used SciPy's optimization routines before, gradient-based optimization is also part of the toolkit there. Now, in this example that we've been using, we had to know how to define the gradient function in Python by hand. That's this function over here. This is all fine and okay if we're only dealing with simple functions, such as the one we've been using in our example. But if we had a complicated math function for which we needed the derivative, then defining the derivative function by hand would be kind of troublesome. Thankfully, if we know how to express our math functions, complicated or not, in terms of elementary NumPy math functions, then tools exist for us to automatically generate the derivative function df. And we call these tools automatic differentiation systems. And in my opinion, automatic differentiation systems are the most important piece to have come out of the decade of deep learning, the 2010s. Now, all deep learning libraries come with an automatic differentiation system built in, but there's only one that is general purpose that also targets the NumPy API explicitly, and this package is called JAX. JAX provides the ability for us as users to write NumPy code and then natively take derivatives of it while also compiling it to native CPU code, GPU, and TPU for acceleration. As an example, just recently I worked with one of my interns to use JAX to accelerate a recurrent neural network 100 times faster than the original implementation in TensorFlow. So today we're going to use JAX because I believe that knowing how to use it will give you infinitely more flexibility when thinking about and implementing deep neural network models. Let's go ahead and see how we can use JAX to optimize math functions. Firstly, from JAX we're going to import the grad function, and then we're going to redefine the math function that we want to optimize. We didn't have to, but this is just for the sake of clarity. I'm putting it over here again. Now, if you look at line 8, this is where the magic happens. Instead of defining df manually, which is what we did up here, right? Over there was where we defined df manually. So now instead of defining df manually, all we do is we pass f into grad, and what that returns to us is another function that we can call on just like we did above to evaluate the gradient. I'd like you to now go ahead and finish up the exercise, confirming for yourself that indeed we can optimize f of w using JAX's grad function. As usual, I will be coding alongside you. Enjoy the music. Let's now make the connection between gradient-based optimization and our linear regression model. In our example, the function we were optimizing was this w-squared polynomial function, and the parameter that we were optimizing to find the function minima was w. Now, in linear regression, the function we're optimizing is the loss function L, which we define as the mean squared error function. Here, the parameters that we want to optimize are w and b. And these parameters, yes, they do show up inside the linear model equation, as you can see over there. But I want you to be extremely clear. We're optimizing the loss function, L, with respect to the linear model parameters w and b, but we're not optimizing the linear model function f. Okay? This is a point of confusion that others have had before, so I want to make sure that this is cleared out of the way. Feel free to pause the video at this point to ponder about it and convince yourself. If you've made it this far, wonderful stuff. You've actually now been equipped with the framework that I'm trying to convey, which is model, loss, and optimizer. So let's write that down. The framework consists of three parts: the model, the loss, and the optimizer. The model is nothing more than a math function f that you can write in NumPy that maps the inputs x to some outputs y. It also has a parameter set theta that controls how the mapping works. And in our linear model, for example, theta would be the parameters w and b. Secondly, the loss is nothing more than another math function that tells us how bad the model is with respect to the data that we have. So it must have the true outputs as well as the model and its inputs. And in our example with linear regression, we're using MSE as the loss function. And finally, the optimizer is a gradient-based optimizer that tells us how to find the parameters that give the minimal loss. So in other words, we're trying to minimize L with respect to theta. And just so we're clear here, L comes from there, theta is this guy, right? Just so that all of the connections are made clear. To get practice, we're now going to code this up together. We're going to start by defining our linear model inside the model function. So let's write it out. Return P of W times X plus P of B. Right. I gave you the answer right there. Let's explain some of the design choices over here. We want P to be a dictionary of values. The reason we want P is so that we can, to be a dictionary, is so that we can index nicely inside there and pull out particular values that we're interested in. Right? So P of W and P of B. X is going to be our input data. And X is going to be the input NumPy array. So we'll do P as a dictionary and X as a NumPy array, and we'll return back a NumPy array. So as I mentioned, we want params to be a dictionary so that we can index nicely into it. So if you remember above, we pick numbers at will, and those form the starting points for the parameters that we wish to change to optimize or minimize our loss function. So what we're going to do here, instead of picking fixed points, we're simply going to draw numbers from a random normal distribution. So we'll do npr.normal over there. Just so that you're aware, we imported NumPy random above at the top of the notebook. So now we finished the model component. We have the model and its associated parameters. Now let's talk about the loss function. Right? So the loss function, let's write the doc strings first. It's going to take in params, which is a dictionary of parameters. It's going to take in X, the input data. Finally, it's going to take in Y, the ground truth outputs. So from the model, we get Y estimate. And what we return is the MSE of the Y estimate against Y. And thankfully, we've defined MSE above already. Right, so this is the differentiable loss function. Remember, everything inside here is defined with NumPy and Python. Everything inside here is also defined with NumPy and Python. So what that means is, well, we can actually define the gradient of the MSE loss simply by calling on grad and obtaining the derivative of the MSE loss function. Okay, so then if we move on, we need to build the optimization routine. Now, something you need to know is as follows. Whatever the function signature is for MSE loss, after you pass it through grad, the exact same function signature applies to the gradient function. What's different is the return statement. MSE loss will return the MSE, so a scalar number, of y versus the model estimates, but demSE loss will return the gradients of the parameters in the exact same data structure as the parameters were passed in. So in this case, from demSE loss, after calling on it and passing in params x and y, we actually get back a dictionary that looks exactly like params. We can use this to our advantage. So the gradient evaluated at each point will be demSE loss of params x, y. So now params, let's give a bit more informative names over here. Params is a dictionary, right? So k is really the name, the key is really the name of the parameter, and p is the parameter value in params. We're going to say params, we're going to do the update now. So name is params name minus grad p of name times 0.0001. Again, just another number. I picked it arbitrarily. Down here, we keep track of the losses. MSE loss is of params xy, which will give us that, and we'll append that into the losses list. Okay, so let's run this guy. And if we plot the loss score over time, it'll go down and trend towards 0. And if we finally print the parameter values, you'll notice, well, we got kind of close, not the best, but close enough. So now, how do we improve upon this? Well, there's a few things we can do. Firstly, if we want the losses to drop faster, we could take a larger step size. So I'm going to do that. Additionally, if we want to get closer to the true value, we can increase the number of iterations. I'm not going to do that because it's a little slow. So we'll just try this one first, this modification first. So we see the losses went down. That's our value of the parameters, a little closer to where we are supposed to be. And finally, simply for confirmation, let's do y_est is model params x plt.scatter of y and y_est. They should form a pretty nice straight line with some, noise still involved. Okay, so let's recap the ingredients. In deep learning, you're always going to need the model specification. These are the equations that help you map x to y. In addition, there are the parameters of the model to be optimized. We call them theta in general. Then there's the loss function that tells us how wrong our model parameters are with respect to the data. And finally, there's the optimization routine, or the for loop that we wrote.
This for loop iteratively modifies our parameters theta such that we minimize the loss.
Welcome back. I hope you're all rested and ready for the next phase of the course, logistic regression. Here, we will build upon what you've learned in the first half on linear regression and extend it to logistic regression, where the model gets changed slightly and we use a different loss function. Let's jump straight into the notebook. Firstly, let's take a look at logistic regression in pictures. In matrix form, The linear regression component should look familiar to you. What we do with logistic regression is explicitly add in an activation function, in this case, the logistic function, which squashes our linear outputs to be between 0 and 1. That is the yellow function g in the diagram. This is also reflected in the neural diagram right below. Let's now do an interactive activity with the logistic regression function. Execute the cell below, and you will be able to explore how the logistic curve changes as a function of w and b. Now that you've had a chance to play around with the function, let's talk a little bit about what w and b control. W controls the slope of the curve. In other words, how sharp the transition is between the 0 and the 1. The larger the magnitude of w, the steeper the transition. Conceptually, b controls the point at which the transition from 0 to 1 happens. So, the higher b is, the more to the left the transition point is, and vice versa. We're now going to explore how we can fit a logistic regression curve to our data using the same set of ingredients, namely model, loss, and optimizer. So now go ahead and execute this cell over here while optionally tweaking the parameters if you so desire. I'm going to do w is -2, b is 5. You should get some simulated data that looks something like this. For logistic regression, let's look at the canonical loss function that is used, the cross-entropy loss. In equation form, the loss function is built up in the following fashion. For each sample, we'll make a prediction, p of I, which we will compare against the ground truth, y of I. So when the ground truth class is 1, and the predicted value is close to 1, we'll get a small number. At the same time, we'll also need to compare 1 minus yi and 1 minus pi. This helps us deal with the ground truth class being 0, where in that case this term goes to 0, and so therefore we're left with this other term on the right. Think a bit now about how the loss function magnitude changes as p of I changes, namely as it goes towards 1 or goes towards 0. For that will give you an intuition onto how this loss function can be minimized as the predictions get better. Now if you're staring at this equation and you're thinking, this looks a lot like the Bernoulli distribution log likelihood, you are absolutely right. That's the connection right there. If you're unclear on any part of the behavior of this loss function, then I'd encourage you to pause the video and think about the following questions. What happens to each of the terms when the ground truth changes from 1 to 0? And what happens to both of the terms when p approaches 0 and when p approaches 1, p being the predicted probability? Once you're ready, unpause the video to go on. Let's now work on the following exercise together, in which we tie together our knowledge of everything we've learned so far. In particular, we're going to put logistic regression in the framework of model, loss, and optimizer. Let's start with the model specification. If you remember, a logistic regression is nothing more than a squashed linear regression. Therefore, we have the linear regression component, and we have the squashing component. Y is equal to logistic of the output, and we return y. Now, if we look at the logistic loss function, first off, keeping in mind, we need to get the predictions out. So preds is logistic model p and x, and what we return is the comparison between the prediction and the output, the ground truth class. So we return the negative sum of y times np.log of preds plus 1 minus y times np.log of 1 minus preds. As usual, with JAX, we don't need to define the derivative over here. I'd probably struggle myself taking the derivative of this function. It's moderately complex. So we can get a computer instead to do that for us. We pass logistic loss into the grad function, and that gives us another function, the d-logistic loss. Now, we also need to define starting points for our parameters. So we'll use the usual numpy random. And we'll put normal starting parameters inside there, normally distributed draws. And finally, we write the training loop. So as usual, we evaluate the gradient at the value of the params. And we start updating the parameters. So let's name these once again a little bit more informatively. So for name, comma, param val in params.items, params of name would be equal to param val minus grad params evaluated at that name times 0.001. And we're going to keep track of the losses over each training loop. All right, let's get going. Oops, where did I go wrong? Here. Let's get going. Right? We print the params. Oh no, we have some null values. Well, what might have happened is that in this logistic loss, our preds, one of them actually got evaluated to 0, and so therefore we get this like loss. We get this extremely. So when you take the log of a 0, well, bingo, good luck, you get a null value. So to fix that problem. This, by the way, is one of those problems that might show up when you're dealing with neural networks. That is, you get null values, and now suddenly you have to figure out exactly where that happened. So in our particular case, we're going to take smaller steps, and that's one way of getting around this null value problem. Let's now see if we've done any better. Looks a little better, more reasonable than what we had just now. You'll notice that the values are often the true value, but we've got the signs correct. I previously had defined W to be a negative value and B to be a really positive value. And the main explanation for this is that we added noise and we rounded off the values. And so if we plot the loss over time, you'll notice it goes down. That's all very nice. When we plot the model prediction against the data, it's not too bad, not too shabby. We possibly could extend the training time, the number of iterations that we fit, then we probably would get a better fit if we extend the number of epochs or the number of loop iterations that we do when training the model.
Great work! Now that you've seen how linear regression and logistic regression work, you're ready to see how neural networks fit in the framework of model, loss, and optimizer. Let's go check it out. Neural networks are a logical and natural extension to logistic regression. In the literature, neural networks are known as a class of universal function approximators, meaning they're flexible and powerful enough to approximate any function that we might desire. Naturally, however, there's a lot of caveats to that statement, but the point holds. They're extremely powerful models. Now, because they're so powerful, the place where we'd use them is essentially where we don't know how to write the mapping between x and y. To give you an intuition of what exactly goes into a neural network model, let's look at one example, the one on the screen. This is an example of what we would call a feed-forward neural network. And the pictures of it below here should look very familiar to you by now. The linear component is colored with red and blue matrices. That's these parts over here. While the activation functions are colored in orange. That's these parts over here and down over here. Now, if you're thinking, wow, this looks just like stacked logistic regressions, well then you're absolutely on the right track. Deep neural network models are more of the same stacked on top of one another. At least that's what the feed-forward models look like. Now, in terms of what the neural diagram looks like, this shouldn't feel too unfamiliar to you. The red W's and blue B's represent the linear transformations, while the orange activation functions do stuff between the outputs, whether it's squashing values between bounds, as the tanh function does, or setting negatives to 0, as the ReLU function does. Let's now see a neural network in action by building one from scratch. The data we're going to work with comes from the UCI Machine Learning Dataset repository. Here, we want to predict whether a molecule is biodegradable or not, given 41 chemical descriptors. The data have been prepared for you, so go ahead and execute the next cell to load the data. Let's quickly inspect the data. This is good practice, by the way. So we're going to do today a quick nullity check just to make sure that everything is all right. So let's make sure that all of the outputs are not null. So pd.isNull of y will give you something that looks like this. And then if you .sum of a bunch of falses, if they're all not null, then it should sum to 0. And that's exactly what we get. Do the same for x. X looks something like this. We'll do a pd.isNull on that. And let's do a sum. We see that all of the columns, none of the columns have any null values. And if we just do a quick sum, to be absolutely sure, yes, none of them have anything null. So that's good. So moving on, we're now going to write a neural network that will take in 41-dimensional data, linearly transform it to 20 dimensions with a tanh function, tanh activation function, and finally, linearly transform it to 1 dimension using a logistic activation function to help model the fact that we have data that are binary, 1 and 0. Now, if you're feeling good about your skills at this point, then feel free to pause the video and fill out the following code cell. Otherwise, feel free to code along with me. Alrighty, so we've got first up over here a helper function called noise, and what it's supposed to do for us is be a convenience wrapper around drawing numbers from a standard normal distribution with easy ways to control the shape of the matrix that's returned. So we need to first initialize our parameters. So let's go ahead. We'll do params of W1 will be a noise of 41 by 20, where 41 corresponds to the 41 input nodes and 20 corresponds to the 20 hidden nodes that we're interested in modeling, constructing our model with. And we need the bias term inside there as well. So params of B1 will be noise of shape 20 comma, so it's a row vector. We'll then do params of W2 will be noise of 20 by 1, and this helps us take us from 20-dimensional inputs to 1-dimensional outputs. And finally, the bias term is always going to be the output number of dimensions. All right. Now let's write the neural network together. First thing we're going to do is return the result of
the first neural network layer. So we'll do this part. Act1 will be equal to np.tanch of np.dot of x with p, the params dictionary, following our convention, w1, and then we'll add p of b1. We call these activations. Activations are the common term for the output from a matrix multiply in the neural network / deep learning world. Okay. Then we'll do the second activation, which is basically our outputs. Act 2 is a logistic transform of np.dot of act 1 with p of w2, and the result added to p of b2 will return act 2. Now, if you're interested in keeping your neural network models well annotated and documented, one thing I would strongly recommend doing is to annotate the shapes on top of, inline, with your model. So let's see. Shapes should be shapes, particularly for x, should be of this convention, where colon represents the sample dimension, i.e. number of rows. Okay? So act 1 would be comma by 20, which is the result of comma by 41 dot 41 by 20 plus a thing that is 20 comma, right? And this sort of annotation has helped me keep my tensor dimensions straight, right? My matrix dimensions straight, because sometimes it's really hard to know what's going on, okay? So this would be act 1, this would be my x, this would be my p of w1, put that up there, and this is p of w2, b1, sorry. All right, and then we'll do the same over here. It's the result of 20, 1 plus 1, comma. This is act 2. This guy is x. P of w2 is that one over there. And this is p of b2. Right? So now we have our tensor dimensions all annotated correctly as well. All right, let's look at the loss function. The piece that we need to define here is preds. So preds is equal to nn underscore model. So we pass everything through the model, p comma x, and we return the logistic loss over there. And we have the d logistic loss, which is the grad of the logistic loss. Fill that in if it's missing on your notebook. Finally, we'll do our training loop. So grad of p is equal to d logistic loss, passing in params x.values and y.values. And finally, we'll do the update steps here. Params name minus grad params name times some small step, and we'll append the loss. So let's see, moment of truth. Oops. Did I miss a W1? No. Oh, my apologies. It's grad P, not grad params. There we go. You can see the loss is decreasing. That's not so bad. And if we do the confusion matrix, that's kind of nice. Here's the confusion matrix plotted as a heat map. And basically, we can see we've learned. We could possibly let the training continue on for a little longer. And if we go on, we expect the loss to flatten out. And we expect our confusion matrix to get a little bit better.
You are a rock star for coming this far. Thank you for soldiering on through the course. I hope it's been illuminating and informative for you. Now, before we end, I want to make sure that we rehash some points that I'm hoping that you take home.
Firstly, the overarching framework here is model, loss, and optimizer. The model is a mapping from input data X to output data Y. It takes the form of a math function f, which we can write in NumPy code, and has parameters theta that we can tweak. The loss function L is nothing more than another math function that quantifies how bad our model is. And finally, the optimizer is a programming routine that iteratively changes theta to minimize the loss function L. I've rank ordered these by how often we modify them, and you should have gotten a taste of that in the course. Let's talk a little bit about that for a bit. Firstly, the model is what we fiddled around with the most. In each of these three examples that we went through, we defined a new model function. By contrast, we didn't change the loss function as often. In the course, we also stopped at feed-forward neural networks, but there are also so-called canonical models for other types of data. For example, image type data, we canonically would use a convolutional neural network, and for sequential type data, we would conventionally use a recurrent neural network. Now, let's talk about the loss function. We changed this only once when we were switching from a regression problem to a classification problem. As you can see, your problem class basically will define the loss function. So for regression problems, we use mean squared error. For classification problems, we'll use cross-entropy type loss functions. Naturally, if the need arises, we can define any arbitrary loss function or modify existing ones using weightings or adding additional terms to it. Finally, let's talk about the optimizer. The optimizer is what we usually don't change. In the course, we wrote a vanilla gradient descent optimizer, but other optimizers are also available. As a matter of practical folklore advice, it's pretty sane to start off with your neural network library's Adam optimizer and put a step size of 0.005. This is folklore that you can say works in my hands, works in many people's hands. That's a trademarked statement. PyTorch and TensorFlow both have the Adam optimizer, and they have a step size that's configurable, and they're all implemented correctly. At the bottom of the notebook is an infographic that I hope you will find useful. It shows how we've progressed from linear models to deep neural networks and the functional matrix and diagram forms of these. I found it very educational when I was making this summary diagram, and I'm hoping that it's extremely educational for you as well. I'd like to end by thanking you for joining me today to get a firmer grasp on the foundational ideas behind deep learning. My hope is that it's going to be extremely beneficial for you in your day-to-day work. In May, I'm going to be launching a monthly newsletter that will bring you a curation of tools, tips, and techniques specifically for programming-oriented individuals to help you learn advanced topics in data science beyond what you might find in the blogosphere. The goal is to go beyond simple copy-pastable code and to go really deep into ideas leveraging your ability to program to help you learn. If it interests you, come join in the fun at tinyletter.com/ericmjl. Meanwhile, you can find my online presence at https://ericmjl.github.io.
Thanks again for your time today, and I hope you enjoy the rest of Virtual PyCon 2020.